Now we are going to discuss the universal law of gravitation. So what is the universal law of gravitation? Every object in the universe attracts each other. Every object in the universe attracts each other, which is directly proportional to the product of two masses. The product of masses of two objects. It is directly proportional to the product of two masses and inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. And this force is acting along the line joining the centers of two objects. I will repeat. Every object in the universe attracts each other, which is directly proportional to the product of two masses and inversely proportional to the square of the distance between them. And this force is acting along the line joining two objects. So we can derive the equation for this universal law of gravitation. For that we have to consider two objects. So let us consider object A and B having mass capital M. A has mass capital M and B has mass small m. A has mass capital M and B has small m. And D is the distance between the centers of these two objects. D is the distance between the centers of these two objects. Okay, then according to the law of gravitation, universal law of gravitation, the force is directly proportional to the product of two masses. So mathematically we can write this statement as F proportional to capital M small m. Capital M is the mass of object A and small m is the mass of object B. So put it as equation number 1. Now the second statement is it is inversely proportional to square of the distance between them. Mathematically we can express it as F proportional to 1 by d square. Inversely proportional to square of the distance. So F proportional to 1 by d square. Put it as equation number 2. Okay, now we can join these two equations because this gravitational force between two objects is taken as F, as that is same. So we can combine these two equations as F proportional to capital M small m divided by d square. That is F proportional to m by d square. So we can remove this proportional sign by putting a constant G, capital G, which is known as universal gravitational constant, which is known as universal gravitational constant. So we can write this equation, the third equation, as F equals G capital M small m by d square. F equals capital G capital M small m by d square. That is F equals G m by d square. So this is the mathematical expression for universal law of gravitation. By multiplying crosswise we will get F into d square equal to G capital M small m. Okay, F into d square equals G capital M small m. Okay, now capital G is equal to F d square by capital M small m. So from this we can find the SI unit of capital G. That means universal gravitational constant by putting the SI unit of force, distance and mass of two objects. So you will get Newton meter square per kilogram square. That means Newton into meter square divided by kilogram into kilogram. So you will get Newton meter square divided by kilogram square. The value of G was found by Henry Cavendish by using a sensitive balance, and it was accepted by all the world and its value is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. The value of G is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. Okay, so this is very important question. State universal law of gravitation and derive the expression for universal law of gravitation. That is very important question. Okay, usually asked. Now this law is universal because it is applicable to all the terrestrial and celestial bodies, whether it is a minute particles like atoms or molecules, whatever it is, to bigger objects in the universe like planets, stars, etc. So it is applicable to all the objects in the universe, whether it is celestial or terrestrial. Okay, and this law is also known as inverse square rule because F proportional to 1 by d square. So this law is also known as inverse square rule. And what are the importance of universal law of gravitation? What are the importance of universal law of gravitation? First of all, we all are binds to the earth due to the gravitational force of earth. Likewise, the tides happens due to the gravitational force between the sun and the moon, isn't it? So that is the cause of tides happens on the surface of earth. Then all the planets revolves around the sun due to gravitational force, and the moon revolves around the earth also due to gravitational force. So that are the importance of universal law of gravitation.
Gravitational force is the attractive force between any two objects with non-zero mass separated by a distance. So does the apple fall towards the earth, or does the earth move towards the apple? Or do both move towards each other? It's actually simple logic. This is the earth, and say this minuscule object is an apple. Based on what we learnt about the gravitational force, both apply an equal force to attract the other object towards itself. So if the forces are equal, which one will accelerate more? Based on the Newton's second law, we know that the force applied is the product of mass and acceleration. So the acceleration will equal force over the mass. The acceleration is inversely proportional to the mass. If the mass is more, the acceleration will be lesser. As the mass of the earth is much more than the mass of the apple, it is the apple that accelerates towards the earth and not the other way around. Hope that makes it clear. Now the question is, how do we quantify this force? To understand this, we need to understand a simple concept. And this simple concept is called the universal law of gravitation. Say there are two objects A and B separated by a distance d. The distance between the centers is considered the distance between the two objects and not this distance. Assume that the mass of object A is m1 and that of object B is m2. As object A is bigger, let's assume m1 to be bigger than m2. The universal law of gravitation says that every object in the universe attracts every object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me repeat. The force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. With this data, we can write it mathematically like this. So if the mass of any of the objects increases, the gravitational force will have more magnitude. And more the distance between the two objects, the lesser will be the gravitational force. Directly proportional to the product of the masses and inversely proportional to the square of the distance between them. This can be written as F equals G times m1 times m2 over d squared. G here is the constant of proportionality and is called the universal gravitational constant. The equation can be modified and written as G equals F times d squared over m1 times m2. The value of G was found out by Lord Henry Cavendish using a torsion balance. The universally accepted value of G is 6.673 times 10 raised to negative 11. What will be the units of G? Force is newtons. As the distance is in meters, we have meters squared. And as the mass is measured using kilograms, we multiply this with kilograms raised to negative 2. This is the value of the universal gravitational constant.
The sun, the stars, everything. It sounds unbelievable, right? But it's true. Stay tuned because you're going to learn more about this on this video on gravitation. And then we'll finish off with our top 3 exam-oriented questions on this topic. Let's start with the basics. When I drop this ball, why does it fall down? It's because Earth is pulling it down with this invisible force called gravity. In fact, the Earth pulls all the objects. That's how I'm standing on the ground or you're sitting. We know that the Earth pulls the moon, the sun pulls the Earth and all the other planets with this invisible force. But the interesting question is, do all bodies pull each other with this invisible force? For example, am I pulling this ball right now? Or are you pulling all the things around you? It may seem strange, but the answer is yes. And this invisible force is called the gravitational force, which we are going to analyze. As we learnt, everything in the universe is pulling everything with this gravitational force. What's the requirement? The body should have mass. The gravitational force is always attractive. So for example, these 2 blocks that I have on the table here are attracting each other with a gravitational force. Let's take a look what this force depends on. Force is directly proportional to the masses. What does this statement mean? So let's say the force between these 2 blocks is 1 Newton. Now if I double this mass, so I'm going to add another block here. So what's going to be the new force between the blocks? That's right, it's going to get doubled. So the force will be 2 Newton. Now let's say we triple this mass. So here we have 3 times of the original mass. Now what is the new force between the blocks? It's going to be 6 times of the original force. So the force will be 6 Newton. So the gravitational force is directly proportional to the product of the masses. Force is inversely proportional to the square of the distance between the 2 bodies. What does this mean? So we saw that the force between these 2 bodies was 6 Newton. Now let's say I double the distance between the 2 bodies. So what will be the new force now? It's going to be 1/4 of the original force. So that's 1/4 of 6 Newton, which is 1.5 Newton. Now let's get these blocks to their original position. Now let's say I half the distance. So when I bring them in, so what will be the new force now? It's going to be 4 times the original force because it's the square of the distance. So the new force is going to be 24 Newton. And this is called the inverse square law. If we combine the relations, gravitational force is directly proportional to m1, m2 by r square, where m1 is the mass of the first body, m2 is the mass of the second body, and r is the distance of separation between the center of masses of the 2 bodies. So if the mass or the distance of separation between the 2 bodies changes, then the force will also change. And that's exactly why I said in the beginning of the video that when I moved from here to here, the distance between me and all the objects inside the universe changes. So the force will naturally change, and that's how I disturb the entire universe when I move from there to here. To convert the proportionality relation into an equation, we need to introduce a constant of proportionality. It has the symbol capital G. So our equation becomes F equal to G m1 m2 by r square, where G is called the universal gravitational constant. Now what's special about it? G has the same value in the entire universe no matter which two bodies you're considering. The value of G will be the same. The scientists measured the value of G. It's really small, 6.67 into 10 to the power minus 11. Now what are the units of G? Well, there's no need for you to remember it. You can easily derive it from the formula we just did. So if you rearrange the formula, we get G equal to F r square by m1 m2. So what will the units of G be? Newton meter square by kg square. Now let's get a feel of the value of G with the help of a simple example. If we take these two books, each having a mass of 1 kg, and let's say they are separated by a distance of 1 meter. So what will be the gravitational force of attraction between these two books? For that, let's use our formula F equal to G m1 m2 by r square. So plugging in the values, we get force as 6.67 into 10 to the power minus 11 Newton. So how much is that? It's going to be 0.000, so we have 10 zeros in there, 667 Newton. So it's a really tiny value. Now, will these two books eventually move towards each other? The answer is no. And it's because this tiny force is overwhelmed by the force of gravity. And of course, there's friction of the table involved. In fact, gravitational force is the weakest force in nature. Let's place the concepts we have learned so far on our concept board. Here is a list of the characteristics of the gravitational force. Let's look at each one by one. 1. The force is always attractive. We know that a magnet may attract or repel another magnet, but the gravitational force between two masses is always attractive. For example, if this is my sun and this is my earth, we know that the sun attracts the earth. But did you know that the earth is also attracting the sun with this gravitational force? 2. Gravitational force is force at a distance. So there's no need of any contact. We know that the earth is far away from the sun. Similarly, when you drop a ball, the earth pulls it down with the gravitational force, but there's no contact between the ball and the earth. 3. The two forces are equal and opposite. So let's say, for example, the sun pulls the earth with a force of 1 billion Newton. So what is the force of the earth on the sun? That's right, it's going to be 1 billion Newton. But then the question is, why is the earth only spinning around the sun? It's because of the smaller mass of the earth compared to the sun. 4. The forces are independent of the intervening medium. We know that there's no medium between the sun and the earth. It's just vacuum. But even if we filled it with an ocean, it wouldn't matter. The force would be unaffected. 5. Independent of the presence of other bodies. So the force between the sun and the earth is not affected by the moon or the other planets. Number 6. The force acts along the line joining the center of the two bodies, or to be more precise, the center of masses of the two bodies. 7. It's a long-range force. So as you keep increasing the distance between two bodies, the force keeps decreasing according to the inverse square law. But the force never becomes zero. So all the things in the universe, the sun, the planets, the stars, are attracting you, and you are also attracting them. 8. Weakest force in nature. As we discussed before, gravitational force is the weakest force in nature compared to other forces such as electrostatic, magnetic, and nuclear forces.